Sometimes we want to express special functions like exponential functions or trigonometric functions in terms of a polynomial. So polynomials are sum of terms consisting of different powers of a variable. For example, this is polynomial in terms of x. So there are varying powers of x, such as x and x squared and so on. Using polynomials, we can make the functions more workable. For example, it is easier to integrate this function instead of this one. And also, using polynomials, we can find good approximations of otherwise complicated numbers. For example, if we want to find the value of, say, square root 1/3 times e to the power of 1/9, we can use the function square root of x times e to the power of x squared and find the polynomial function of this and sub in x to be 1/3 to find the value of this. Now the question is, how do we transform these special functions into polynomials? We can use the Maclaurin expansion to do this. Let's take a function f of x. Now, Maclaurin's theorem states that if this function is infinitely differentiable at x equals to 0, then the function can be expressed as a polynomial with ascending powers of x going on forever. But if we want to find a function, we need to find the coefficients. To do this, let's first find the first coefficient, a0. To do this, we need to remove the other terms. As such, we can set x to be equal to 0, leaving us with a0. Therefore, a0 equals to f of 0. Next, to find the second coefficient, we need to remove the first term as well as the rest of the terms. To do this, we can differentiate the function to get rid of the first term, as constants will become 0 if we differentiate it, and remove the x in the second term. Therefore, again, we can set x to be equal to 0 and obtain the second term. a1 equals to f prime 0. We can do the same thing and differentiate again. As this is a constant, it becomes 0, and we can remove the x in the second term. And again, set x to be equal to 0, and thus we're left with the second term. Thus, a2 is equal to the second derivative of f0 over 2, since there's a 2 here. Let's again differentiate the function to get the fourth term. Thus, this becomes 0, and we remove the x in the second term, leaving us with 3 times 2, a3. I think it's pretty clear that a3 is equal to the third derivative of f of 0 over 3 times 2. And thus we can begin to see a pattern. a4 is equal to the fourth derivative of f of 0 over 4 times 3 times 2. And we can see that the rth term is equal to the rth derivative of f of 0 over r factorial, because r factorial is equal to r times r minus 1 times r minus 2, so on until 1. As we can see, this is 4 times 3 times 2 times 1, 3 times 2 times 1, 2 times 1, and this is just 1. So basically, any function fx can be expressed as f of 0 plus f prime of 0 over 1 factorial, which is just 1, x plus second derivative of f of 0 over 2 factorial x squared plus third derivative of f of 0 over 3 factorial x3, and so on. And the rth term will be the rth derivative of f of 0 over r factorial times xr, and so on. and this can be done infinitely many times. Thus, we can express any function as an infinite polynomial. Now, let's use this equation to find polynomial forms of special functions. First, let's find the function ex in terms of polynomial. We know that f of 0 is e to the power of 0 equals to 1, and we know that fx is equal to f prime x, and so on, because if we differentiate e to the power of x, we still get e to the power of x, and this can be done infinitely many times. Therefore, f prime 0 is the same 1, and everything will be 1. Thus, if we want to express e to the power of x as a polynomial, we can get e to the power of x equals to f of 0, which is 1, plus f prime 0 over 1 factorial, which is just 1, times x, plus this 1 over 2 factorial, half 1 over 2 factorial times x squared. This is just 1, and everything becomes 1. So this is the polynomial of e to the power of x. Let's find the polynomial version of sine x. We know that if we differentiate sine x, we'll get cosine x. If we differentiate this again, we'll get minus sine x and minus cosine x, and then back to sine x. Since this is fx, this will be f prime of x, second derivative of x, third derivative of fx, and fourth derivative of fx. If we set x to be 0, sine of 0 is 0, cosine of 0 is 1, minus sine 0 is 0, minus cosine 0 is minus 1, and so on. Therefore, we can see that it alternates between 1 and minus 1. Thus, if we were to express sine x as a polynomial, we'll get f of 0, which is 0, plus f prime 0 over 1, which is just 1, x, plus 0 again, so there's no x squared, and then minus 1 over 3 factorial, 0 times x fourth, which is just 0, so there's also no x fourth, and then 1 over 5 factorial of x to the power of 5, and so on. Then if we rewrite this, we can see that there are no even powers of x. So it's only x to the power of 1, x to the power of 3, 5, 7, and so on. And also, the signs of the term alternate between powers of x. And for the general term, we can express it as minus 1 to the power of r times x to the power of 2r plus 1 over 2r plus 1 factorial. For example, for x to the power of 3, we can put r as 1, so that minus 1 to the power of 1 is minus 1 times x to the power of 3 over 3 factorial. As for 5, we set r to be 2, so that the first term will become minus 1 to the power of 2, which is just 1. So it's plus, and so on and so forth. For cosine x, it's similar to sine x. We differentiate cosine x, we get minus sine x. Then we differentiate this again, we get minus cosine x and sine x and cosine x. So this is fx, this is f prime x, this second derivative of x, third derivative of x, and fourth derivative of x. Therefore, if we want to express cosine x as a polynomial, we get f of 0, which is 1, cosine 0 is 1, and then f prime 0, which is just 0, so there's no x variable, and then second derivative of f of 0, which is minus 1, minus cosine 0, so minus 1 over 2 factorial x squared, and then so on. So in cosine, instead of not having even powers as sine, there's no odd powers. So there's only x squared, x to the power 4, x to the power 6, and so on. And also, the powers between the terms alternate. As such, we can write the general term as minus 1 to the power of r times x to the power of 2r over 2r factorial. Now let's use graphs to better understand how these approximations work. If we draw the graph of e to the power of x, we will get this. If we were to draw the graph of 1 plus x squared over 2, we'll get this graph. You can see that it slightly touches the graph of e to the power of x, and thus can be useful to approximate e to the power of x for around this region. However, if we want a more accurate approximation of e to the power of x, we can also add the term x cubed over 3 factorial. And when we draw the graph, we'll get something like this. And as you can see, it's getting closer to the graph of e to the power of x. And in this range, it's going to be very accurate. However, if we want it to be even more accurate, we can add x to the power 4 over 4 factorial, or 24, and we'll get this graph, which touches the graph of e to the power of x even more. Thus, to conclude, the more terms we add to the polynomial, the more accurate the approximation to e to the power of x is. This also applies to sine x and cosine x, and you can try it for yourself to see that if we add more terms, it will become more accurate. Now, using the identity sine x equals to x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, and so on, and cosine x equals to 1 minus x squared over 2 factorial plus x fourth over 4 factorial, and so on, we can find a good approximation of sine x. If x is a sufficiently small angle, say 0.01, then higher powers of x, such as x cubed and x fifth, will become negligible, close to 0, and therefore we can set sine x to be approximately x. For cosine, it is agreed that when x is sufficiently small, then x to the power 4th and higher powers of x will become negligible as well, and thus cosine x can be approximated as 1 minus x squared over 2. This approximation is useful in calculation problems. However, sometimes it is difficult to determine what angle is considered small. Usually, angles below 1 radian is sufficient to be small. And conventionally, if x is a small angle, then the multiple of x, such as 2x, 3x, would be small as well. And therefore, we can also apply sine 2x to be approximately 2x and cosine 2x to be approximately 1 minus 4x squared over 2, which is 1 minus 2x squared, and so on. So this is Maclaurin's series.